In the last lecture, we had introduced certain elements which we called as the gates, which work on single qubit, 2 qubits and 3 qubits, and essentially what we said is a few of these elements are good enough to construct what we will call as the quantum circuit as we go along. So let me just review for you these elements. For example, what happens to a 1 qubit gates. So basically, as we have seen, since a single qubit can be represented as a point on a block sphere, so basically all operations which take one point on the block sphere to another, which consists of the rotations and reflections which will take a point on the sphere to another point on the sphere, are permitted. And in general, we have seen in our representation of the gates by means of matrices, since a single qubit state is represented by a column vector with 2 components, my operators or the matrices corresponding to single qubit gates will be 2 by 2 matrices. I will just be mentioning again, because we will be coming across them regularly, some more common gates. For example, the Hadamard gate or H gate is a gate which takes the state 0 to state 0 plus 1 by root 2, and to state 1 it takes to 0 minus 1 by root 2, and with our matrix representation 0 being given by 1 0 and 1 being given by 0 1, the representation for the Hadamard matrix is 1 over square root of 2, 1, 1, 1 and minus 1. So this is an important gate in which acts on a single qubit state. There are others which we have mentioned last time, but let me talk about X gate. X gate is simply given by 0 1 1 0, is standard Pauli matrix, and its job is to take the state 0 to state 1 and vice versa. So this is basically equivalent to a classical NOT gate. Like X gate, we have Z gate, which changes the sign of the component 1, and also we have a Y gate which is given by a matrix very similar to the Pauli Y matrix. I will write it down because there seems to be different notation slightly. So Y gate is generally written as 0 minus 1 1 0, though my sigma Y is 0 minus I 0, but it is a matter of simply putting in another constant I in front of that, so it should not really cause any confusion. And of course we have Z gate which is given by the Pauli Z matrix, which is 1 0 0 minus 1. So these are the more important 1 qubit gate. So talking about 2 qubit gates, the most significant of them is what we call as the controlled NOT gate or C0 gate. If you recall what C0 gate is, that a C0 gate basically has a control and a target. So its representation in circuit is like this. So if control is equal to 0, target remains target, no change. If control is equal to 1, the target bit is flipped, that is 0 becomes 1 and 1 becomes 0. So if C is equal to 1, target is flipped. We also talked about a few 3 qubit gates. The first one was a Toffoli gate, which is also known as a CC NOT gate, control NOT gate, represented like this. So basically, the target bit, which is this has two controls. The target bit will be flipped if both this control and that control happen to be equal to 1, and nothing happens to the target bit if one or both of them happen to be equal to 0. And finally, we had talked about a controlled swap, C swap, which is also called a Fredkin gate. So basically, a Fredkin gate again has a control, but there are targets on which it will act, and so this will essentially flip the targets. So this is your control, it will flip the target if the control bit happens to be equal to 1. So these were the elementary gates which we talked about, and what we are going to do today is to talk about quantum circuits, which basically consists of the gates work on the inputs and then finally of course give rise to an output. So let us look at some of the implementation of the classical circuits based on that. So if you look at the slide now, you notice that the classical NOT gate, which is actually the only reversible classical gate, is essentially remains the same NOT gate, because all that you need is a unitary matrix corresponding to the Pauli X gate, and so therefore if the input bit is A, then X gate acts on it and it becomes an A bar. Look at XOR. XOR, as you know, is addition modulo 2. That is only if we are talking about one of the bits to be 0, the other bit to be equal to 1, then only we get 1, otherwise we get 0. So this is same as addition modulo 2, and which is nothing but a C0 gate. So as you can see it, that supposing I have this as the bit A and this as the bit B. So this is A, and this is obviously A XOR B. So this is addition modulo 2 or the XOR. Referring back to the slides again, you look at the right hand side of this picture. If you look at the right hand side of the picture, I have given the implementation of XOR using a CC NOT gate. So look at this. So for example, what happens here is that one of the controls I have set as the bit 1, another control is X. So therefore, the CC NOT gate, the target will be flipped only if X is equal to 1. So therefore, the product must be equal to 1. And so the Y then becomes Y plus X, because if X is equal to 0, then of course this is simply Y XOR 0. And so therefore, either of these can be considered as an equivalent of the XOR gate. Now a CC NOT gate can be used to implement a classical AND gate. So you look at what we have done here. I've got two controls as we said. So therefore, these two controls can be in principle A and B. And what we have done is the target bit we have put to be equal to 0. Now remember, 0 XOR anything, okay, is the same thing itself. So therefore, if I am having both the controls, namely A and B equal to 1, then my target bit becomes 1, and that is what a classical AND always does, because A into B must be equal to 1. So let's go to the general idea of what is a quantum circuit. So basically, a quantum circuit contains logic gates, and there you will notice that I have been connecting these various logic gates by means of straight lines. Now in normal classical circuits, these straight lines represent wires and physical wires. Now, in this particular case, in case of quantum circuits, or they need not stand for any physical wire, but they essentially indicate the direction in which the logic flows. The essentially what we are saying is, you should have the input at the extreme left most part of the circuit. Then as time progresses, we continue with the application of logic gates in the same order in which they come, and that is always logic flows with the earlier time being to the left. Now, there are some restrictions. Remember, in a classical algorithm, we allow what are called loopings or fan-ins as they are called. So basically what we do is that you can loop a particular logic. Now, this is not permitted here, because as I told you, the diagram essentially represents a flow of logic with time. Now, if you allowed the looping, then of course it would mean you have to travel back in time. So therefore, unlike classical circuits, looping is not permitted in a quantum circuit. So inputs are qubits, the outputs of course are also qubits. Now, unless otherwise stated, very expressly stated, the qubits are usually expressed in computational basis. This is not a requirement for a quantum circuit, but this is what the traditional practice is. So therefore, we have said, now sometimes what happens is, you want to make your measurement in, for example, a bell basis instead of a computational basis. But then somewhere we must state that that is what is happening. Going back to the slide, what we said is looping or fan-ins are not permitted. In other words, you can't have several inputs giving rise to the same output. Now, the point is this, that the inverse process of that is the fan-out circuit. Now, fan-out circuit is basically a copying circuit. So therefore, as we will see later in this lecture or the next, depending upon time, a quantum circuit which copies a state to another state, a general state to another state, is not permitted by a theorem known as the quantum no-cloning theorem. And as a result, fan-out is not permitted. Now, if fan-out is not permitted, then of course its inverse or the reverse, fan-in, which is also not permitted, because as we know, quantum computation happens in a reversible manner. So let me give you an example of a specific quantum circuits, namely a quantum half adder. So as you know that basically I have this problem. I want to add two single qubits or even C bits, classical bits. But then when the two classical bits are equal to 1, then I have a carry. So half adder essentially gets the sum, which means 1 plus 0 must be equal to 1, 0 plus 0 must be equal to 0, and 0 plus 1 is of course equal to 1 again, but 1 plus 1 is 1 0, which means my sum must be 0 and my carry must be 1. So a half adder circuit has essentially this situation. So let's look at how does a half adder circuit work. So this is A and this is B, and what I do is I set this third one to 0. Remember, each one of them is a single qubit, so A and B can take value 0 or 1 each. Now I start with a circuit which is a CC NOT gate. So notice, remember what is the CC NOT gate. So a CC NOT gate would interchange or would flip this bit 0 to 1 only if both A and B are equal to 1. But remember, a CC NOT gate does not do anything to the control themselves. So therefore, this will remain A and this will remain B. And this is at this stage, at the end of the CC NOT gate, what I get is a 0 plus AB. Now 0 plus AB, what is this? Now notice that AB has a product 1 only if both A and B happen to be equal to 1. So therefore, this will be XOR of 0 with 1 giving me 1. So if A and B each equal to 1, the last bit here would essentially have the carry. Because 1 plus 1 in binary addition is 1 0 and this is your carry. There is no carry if either A is 0 or B is 0 or both are 0 of course, because in that case I get equal to, because it is an XOR operation, I get equal to 0. But notice what is happening here. This is still A and this is still B. So supposing with A as the control and B as the target, I apply a single C NOT gate. Now this is nothing but A XOR B. So therefore, when A is equal to 0, B is equal to 0, I of course get 0. A0 B1 or B0 A1, I get 1, which is what I expect from an addition. And if both A and B are equal to 1, then 1 XOR 1 is equal to 0. So this is my sum. So this is the way we implement half adder. You can do some practice on this type of implementation of classical circuits. For example, try what is a full adder and things like that. Now, there is another important component of a quantum circuit. Before we write down a full-fledged quantum circuit, we need to understand this a little bit. And this is what is known as an oracle. Not to be confused with the corporations having the same name. Oracle, as you know, is what old saints and people like that used to essentially predict, or as is occasionally known as the Akashvani or whatever we learned from heaven. Now, what is an oracle? The oracle in quantum computer has a very specific purpose. Very often we want to compute some functions, and what we do in classical computing is this: we give a subroutine call. Now remember, these subroutine calls, we simply say call this. What is assumed is that there is an algorithm corresponding to that available as a part of the program. Now an oracle essentially does the same thing. So basically an oracle is something which takes in certain amount of input, computes the function. We at this moment do not care how it does it, but we assume that there is a quantum circuit which is enabled and which can compute this function and gives outputs the corresponding result. So therefore, it is like a black box. So oracle is represented like this. It's a black box. So suppose I am computing a function which you need not worry about what that function is at the moment, all done by unitary operation. The whatever is the unitary operator computing this function is appearing at the center of this. Now, one of the inputs here is x. Now, so the x is an input. So let me look at the slide again. Now, there is a secondary or an auxiliary input, occasionally called ancilla. This is y. So this is ancilla. Also the target bit. This is where the output will be there. Now, this UF function takes x as the input, computes fx and outputs here, leaving the input the same. So this is unchanged. And here what you get is the XOR of y with the fx. So this is the way an oracle is represented. Now you notice that supposing you set y equal to 0, which means this is 0 plus fx, which by definition is fx. So therefore we compute the fx itself. If you take y is equal to 1, this is 1 plus fx, 1 XOR fx, which is nothing but the complement of fx. Now, so this is how an oracle is represented. But that's not the only thing that it does. Remember that our biggest power of a quantum computing was the superposition principle, that is quantum parallelism. So the quantum parallelism says that the computation of fx corresponding to x need not be restricted to one particular value of x, that is one particular state. So supposing instead of a single state, I have a linear combination of states, then my fx will be computed for every component of that linear superposition. Just to give you an example, that suppose the x that we talked about here, so the x that we talked about here, supposing was an n qubit input. Now, what happens to this n qubit input if you send each one of these lines? Remember, n qubit inputs is basically n number of lines like this. We normally, if we write like this, a single line will do. Now, supposing each one of them I pass through a Hadamard gate. Then what I get here is, remember, my 0 becomes 1 over square root of 2, 0 plus 1. So therefore, for instance, what happens to 0 into 0, that is 0 square, pass through 2 Hadamard gates. So this will be 1 over root 2 square, 0 plus 1 multiplied by 0 plus 1. And what is this? This is equal to 1 over 2, 0 0 plus 0 1 plus 1 0 plus 1 1, which is nothing but a linear superposition of 2 qubit basis states. Remember, the single qubit basis states are 0 and 1. The 2 qubit basis states are 0 0 0 1 1 0 and 1 1. So this is the uniform superposition. Uniform meaning each one of them comes with the same strength. Uniform superposition of 2 qubit basis states. Now, extending this, if you have n number of zeros and pass them through Hadamard gate, n of them, then what you get is 1 over square root of 2 to the power n sum over x, where this x that I have written down here is the uniform superposition of n qubit basis states. This is a very important result because this uniform superposition of n qubit basis states we will be using quite frequently in our discussion. So therefore, suppose I pass my this thing through Hadamard gate, of which my input was the linear superposition, then my whatever function I am calculating is calculated corresponding to each one of them. The last component of quantum circuits is the process of measurement. As I have said already that the process of measurement we assume to happen always in the computational basis. Look at the slide. So the measurement process is represented by a meter like symbol, and so notice that even if my input, or we are measuring an output which is a linear combination, when I make a measurement, the measurement comes up with certain probability. So this gives you one of the possible results of the outputs. Now we will see that this has a lot of importance. So therefore, the quantum circuit consists of input, the logic gates, the oracle, and the measurement meters. So this is the complete quantum circuit, and we will be talking about specific quantum circuits as we go along in this course.